Hello friends, in this video I'd like to solve the following problem from the Serbia and Montenegro Balkan Mathematical Team Selection Test 2005, problem number 2. We wish to find the number of 100-digit numbers whose all digits are odd and in which every two consecutive digits differ by 2. So it's a problem from combinatorics. It's a very nice problem. Here are my hints. Let AN, BN, CN, DN, and EN denote the number of n-digit numbers ending in 1, 3, 5, 7, and 9, respectively, whose all digits are odd and every two consecutive digits differ by 2. So we are defining 5 sequences and find recursions for every of this sequence and try, and it's possible to find the general result for this recursion, but it's probably easier to write a bunch of terms and to see the pattern emerging. And once you see the pattern, write your guess and try to prove it by mathematical induction. So I'll give this problem a try and I will see you in a minute. Okay, so as I suggested, I will let my 5 sequences be defined. And now I will try to define my recursions. So let's start with AN, BN, CN, DN, EN. Okay. AN, the number of n-digit numbers with all the digits ending in 1, whose every two digits differ by 2. How many of them are there? Well, I have n digits. Yes, n digits. The last one is 1. So the digits just before it must be 3. It's the only possibility for them to differ by 1. So it's really the same as the number of n-1 of numbers with n-1 digits, all the digits, whose last digit is 3. But what is it? It's by definition bn minus 1. bn minus 1. Okay. What about last digit 3? Then we have two options. The penultimate digit can be either 3 or 5. If it's 1, the number of numbers ending in 1 is an minus 1. And if it ends in 5, it's cn minus 1. The same will be true for cn. Cn is bn minus 1 plus dn minus 1. dn is cn minus 1 plus en minus 1. And slightly different will be the end, en, because if the last digit is 7, the penultimate digit must be 9. So we have, the other way around. If the last digit is 9, the penultimate digit must be 7. So it's dn minus 1 ways to do it. Okay, so that holds for n greater than or equal to, and we need initial conditions, which are trivial, because we have numbers with 1 digit, so it's 1, 1, 1, 1, 1. Nothing special here. Sorry, Polish. not dla, but for. Okay, very well. What now? Well, now it's possible to eliminate, to simplify this system of recursions, but it's probably easier to write a bunch of terms and try to see the pattern. So, you know what? I will copy. Oh, I will write it once again. So let's start with A1, B1, C1, D1, E1. Okay. A1, B1, C1, D1, E1. It's 1, 1, 1, 1, 1. Now, what happens for 2? A2, B2, C2, D2, A2. Well, A2 A2 is B1, so it's 1. What's B2? B2 is A1 plus C1, so it's 2. What is C2? It's 1 plus 1, 2 as well, D2 is 2 as well, 1 here. Nothing obvious yet. A3, B3, C3, D3, E3. Well, what is A3? A3 is B2, so it's 2. What's B3? B3 is A2 plus C2, so it's 1 plus 2, 3. What is C3? It's 2 plus 2, so it's 4. What's D3? D3 is 2 plus 1, 3 again, and 2. Okay. Next. A4, B4, C4, D4, E4. So A4 is B3. Here we have 2 plus 4, 6. 3 plus 3, 6. 4 plus 2, 6. And 3. Let's write our next term. Again, if you see the pattern at that moment, you can skip to writing general formula and proving it by induction, but I wish to do more terms to make my pattern clearer. So next, A5. A5 is B4, so it's 6. Then 3 plus 6, 9. 6 plus 6, 12. 9, 6. And maybe I will write 2 more iterations. I will write A6, B6, C6, D6, E6. So now I have 9, then 6 plus 12, 18, 9 plus 9, 18, 18, 9. And maybe one more, A7, B7, C7, D7, E7. A7, it's 18, then we have 27, then we have 18 plus 18, 36, 27, 18, and you know what, I will do more iterations, we have time. You can fast forward, if you wish. Now we have A8 is 27, 54, 54, 54, 27, and really the last iteration, A9, B9, C9, D9, E9 will be, if I'm not mistaken, 54, 27 plus 54 is 81, then we have 54 plus 54, 108, 81, 54. And so on. Okay, now time to see the pattern. Well, we have two cases really, because for even indices we have something like 2 outliers and 3 middle terms the same. For example, 3, 3, 6, 6, 6, 9, 18, 18, 18, 9, and so on. So maybe let's guess first the general term, the general form of terms with even indices. Well, if you look at it, each time we have 1, 3, 9, 27, we are multiplying by powers of 3, at least A and E. So my guess is that for every positive integer n, A to n equals E to n, I guess that it's 3 to the power n minus 1. For example, if n equals 1, we have A2, it's 3 to the power 0, it's 1. And middle terms are twice as large. So I also guess that B to n, C to n, and D to n equals 2 times 3 to the power n minus 1. That's my guess for now. That's my guess. Let me move it to the left. Yes, that's my guess. And my second guess for odd indices, Well, what about the odd indices? Well, what can we notice? Apart from the first terms, which is 1, 1, 1, 1, we have 2, 6, 18, 54. We are multiplying by 3 each time. So I guess that my term a2n plus 1 and e2n plus 1 is 2 times 3 to the power n minus 1. For example, for n equals 1, I have a3 equals 2. It is. Okay, what about b 2n plus 1 and d2n plus 1? Well, let's take a look. Well, it's what exactly? It's 3 over 2 times as large as a term. Yes, for example, 18 times 3 over 2 is 27. So I multiply this by 3 over 2, so it's 3 to the power of n. For example, for n equals 1, b3 equals 3. It is. And what about the c term, c2n plus 1? c2n plus 1, well, it's twice as large as an. So it's 4 times 3 to the power n minus 1. Let's make it a little bit smaller. Okay, and this pattern does not hold for n equals 1. These cases are outliers. But I have started my variable from n equals 1, so I have a3 and so on. a1 is not included. So it's my claim. My claim has really two parts, and I will prove them separate. I will prove them by induction. Let me put it a little bit lower. Basically, it's my claim. Once we prove it, we are almost done, but we need to prove it by induction. Proof by induction. Well, we have noticed that it holds for case of 2 and for case of 3. So, by induction, it holds, it is true for n equals 1. Both parts of my claim are true for n equals 1, because a2 and a3 and so on were verified already. So now suppose that both parts of our claim are true for some positive integer n. And now I wish to check what happens at a plus 1. So maybe let's consider two cases. Case number 1. Case number 1, n is even. N equals to m for some positive integer m. I wish what happens at a n plus 1 and so on. No, we don't need to write them because we have n in our indices. So we have n already here and here. So okay, so now let's verify a2n plus 1 and a2n plus 3. a2n plus 1. What is a2n plus 1? a2n plus 1, it's by our recursion, it's b, so it's a to n plus 2, so it's b to n plus 1, and by our inductive assumption, b to n plus 1, it's 3 to the power of n. 3 to the power of n. So it's 3 to the power n plus 1 minus 1. What about b to n plus 1? b to n plus 1, by our recursion, b to n plus 2, it's a to n plus 1 plus c to n plus 1. So that's, and by our inductive assumption, a to n plus 1 is 2 times 3 to the power n minus 1, and c to n plus 1, it's 4 times 3 to the power n minus 1, and that can be written as, we have 2 plus 4 is 6, but 6 is 2 times 3, so it's 2 times 3 to the power of n, but power of n can be written as n plus 1 minus 1. C to n plus 1, it's c to n plus 2, b to n plus 1, d to n plus 1. Let's take a look. b to n plus 1 and d to n plus 1 are both 3 to the power of n. So it's 2 times 3 to the power of n, but that's exactly the same as 3 to the power n plus 1 minus 1. d to n plus 1, it's d to n plus 2, and it's c to n plus 1 plus e to n plus 1. So it's c to n plus 1, it's 4 times 3 to the power n minus 1. And what about e to n plus 1? It's 2 times 3 to the power n minus 1. So it's 6 times 3 to the power n minus 1. And again, as in the second case, it's that. And finally, 2n plus 1 equals, by our recursion, it's e to n plus, it's e to n plus 2, and it's by our recursion d to n plus 1, and d to n plus 1 is 3 to the power of n. And 3 to the power of n is 3 to the power n plus 1 minus 1. Okay, we are halfway there. Now we need to check what happens for a to n plus 1 plus 1, b to n plus 1 plus 1, c to n plus 1 plus 1, e, d. You know, it's rather boring, but it's important. If you are preparing for some mathematical Olympiad, induction is very important. It needs to be rigorous. So I'm doing it rigorously. So here we have a to n plus 3, b to n plus 3, c to n plus 3, d to n plus 3, e to n plus 3. A to n plus 3, well, by our recursion, it's b to n plus 2. And we have already verified that b to n plus 2, it's 3 to the power, it's 3 to the power n. It's 3 to the power of n, just because it was, am I right? No, b to n plus 2 was 2 times 3 to the power of n. Okay? b to n plus 3, it's a to n plus 3 plus c to n plus 2 plus 2. By our previous part, this is a to n plus 2, it's 3 to the power of n plus 2 times 3 to the power of n, so it's 3 to the power n plus 1. Okay, very well. Now, next, it's c to n plus, so it's b to n plus 2 plus d to n plus 2, which is b to n plus 2 is 2 times 3 to the power of n, d2n plus 2, it's 2 times d2n plus 2, it's 2 times 3 to the power of n as well. So it's 4 times 3 to the power of n. And then we have c to n plus 2, e to n plus 2. So it's c to n plus 2. It's 2 times 3 to the power of n plus 3 to the power. So plus 3 to the power of n, yes, it's right. 3 to the power n plus 1. And finally, en to n plus 3, it's d to n plus 2, and it's 2 times 3 to the power of n. And that closes our inductive proof, because it is exactly what we wanted. Show that 2n plus 3, a to n plus 3 is 2 times 3 to the power of n, it is. Then it's 3 to the power n plus 1, it is. And finally, 4 times 3 to the power of n, it is. It closes our inductive proof. And that finally, after all of that, what we really want is a100 plus b100 plus c100 plus d100 plus e100. And how can we find it? Well, a100 is a 2 times 50, b 2 times 50, c 2 times 50 plus d 2 times 50 plus e 2 times 50. And what's that? Well, that is, let's use our theorem, our claim. A100 is 3 to the power 49. Then we have B100, C100, and D100 is 2 times 3 to the power 49. And finally, we have 3 to the power 49. So all in all, A100 plus B100 plus C100 plus D100 plus E100, our result is 8 times 3 to the power 49. And that is our answer, because it's the total number of 100-digit numbers which end either in 1, 3, 5, 7, or 9. 8 times, and whose digits differ by 2. Every 2 digits differ by 2. 8 times 3 to the power 49. Quite a large number, I say. So, yes, thank you for watching, and I will see you next time. Goodbye.